Today, we're talking about hidden Markov model. This is a computational approach that has been widely used in computational biology. So we will first go through what is Markov chain, and then explain what is hidden Markov model, and then we'll teach you how to use this to do some inference. In order to understand Markov chain, we first need to understand independently and identically distributed events, which are events that are not correlated with each other. Basically, the current event has no predictive power of future events. For example, the probability a couple had a boy as their first child to infer the probability of the next child being a girl is the same as the probability of having a girl in the first place. You know, whether the previous baby is a boy or girl doesn't matter. And supposedly you have a fair coin and you're asking, what's the probability that I'm going to use this coin to flip a head, knowing the previous flip is a head. Again, this is IID because the previous coin doesn't really matter. It's always the same probability that you will flip a head at this time. And also, if you have a dice and it's kind of a fair dice, you know that the previous dice throw is a 5. You know, the likelihood that you're going to get a 1 is the same as the 1 by itself. And so that's IID. And in order to understand discrete Markov chain, we also need to understand what is a Markov process. And so in this process, we have distinct states, which in the previous example would be the dice having, you know, like different heads or the different numbers and so on. But also we have regularly spaced discrete times, such as day 1, day 2, or the first row and the second row. And so in a Markov chain, instead of IID, where one event has no effect on the future events, in Markov chain, future states can be dependent on the current state. But depending on the level of Markov chain, it can be dependent on just the present state or 1 level before or 2 level before. So that would be like a first order Markov chain, second order Markov chain. But before that, it doesn't have effect. And so let's think about a very simple first order Markov chain, which means the future state only depends on the present state, 1 state, but not any state before, any way to get here. So to write this in an equation, it means that the probability at time t that you will get to a particular state, knowing all the previous events, we see that this is only dependent on the t-1 event. And so the t-2, t-3, all the previous events doesn't matter, but the t-1 event has some influence on the current state. And this is something called a transition probability, which is often written as AIJ, which is, you know, knowing that the t-1, you get a state I, we want to know what's the probability at time t, we will get to a state j. And so because this is a probability, all the numbers should be larger than or equal to 0. And imagine in the t state, in the t time, if there are overall X number of options, the total option together should add up to 1. And so this is the transition probability. And so in a Markov chain, we can imagine the following situation. So if we know a student has exam grade for the previous exam as a pass, and so the states could be just pass or fail. The discrete times would be exam 1, exam 2, exam 3, and so on. And imagine we have the following state transition. And so this would mean that if the student has passed exam 1, the likelihood that they will pass again will be 0.8, but the chance they will fail is 0.2. But if a student failed that first exam, their probability of passing is only 50% and failing is also 50%. You can see here, these two numbers add up to 1 and these two numbers add up to 1. So we can ask, given the student has this track record, so like in 6 exams so far on a course, they had pass, 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 fail, 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 the probability of passing the next exam is, you know, the 7th exam being a pass, given the transition probability and all the string of events that has happened, we will say that, okay, it depends on the transition probability. And because this is a Markov chain, which only depends on the previous one exam, then we know that the previous exam is a fail. And therefore, looking at this transition probability, we know that there's a 50% chance failing again. Another example for the states, we have rain, cloudy, and sunny days. This is weather. And the discrete time is day 1, 2, 3, 4. And we have the following transition probability. If you have rainy day, there's a 40% chance it will rain again, 30% chance cloudy, and 30% sunny. If it's cloudy, 60% chance it will be cloudy again, but 20% chance rain or sunny. And if it's sunny, it's 80% sunny again and 10% each for rain and cloudy. Of course, this is a completely artificial transition matrix. But imagine we have a transition matrix like this. We can say that given at day 1, we have a sunny day, what's the probability of observing the following string of events, which is sunny, 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 rain, rain, sunny, cloudy, and sunny. And knowing that the first day is a sunny day, we just ask, what is the probability we will have a sunny day again? That's transition A33, it's 0.8. And then from second day to the third day, again, is transition A33, is again 0.8. And then from sunny to rain, it's A31 is 0.1, and then 1 to 1, or rain to rain, is 0.4, and then rain to sunny again is 0.3, and then rain to cloudy is 0.1, and cloudy to sunny is 0.2. And so you can calculate that probability. So you can see if these types of transition probabilities are given, we can predict the likelihood certain string of events are going to happen. And the third example is a case where you use a coin to flip, to decide to pick coins. So supposedly we have a fair coin, that's one state. Another coin is a biased coin, B. And the discrete times is, you know, you are using a fair coin versus an unfair or biased coin. We introduced this new concept of initial probability, which is what's the likelihood that I'm gonna just use a fair coin in the first place. It's 0.4, and and also the initial likelihood of using a biased coin is 0.6. And also for the transition probability, we can write it as a matrix like this, but you can also imagine writing it something like this, which is if I'm already using a fair coin, the likelihood I will use a fair coin again is 0.9, or I use another coin, the biased coin, which is 0.1. But if I'm on the biased coin, 70% chance I will use the same coin, but 30% chance I'm gonna flip to the fair coin. And so now I can ask the similar question. What's the probability of fair, fair, bias, bias, fair, 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 biased? And so the difference from the previous example is that we know at time 1, the state is sunny, whereas in this case, we don't know the initial state. Therefore, we first start with what's the probability of seeing a fair coin in the first place. And we know that is 0.4. And then after that, it will be the transition probability from fair to fair, fair to bias, bias to bias, bias to fair, and so on. And you just multiply the probability. And so that's kind of how Markov chain works.